This is the week 5 of the problem solving session in the course of Fundamentals of Micro and Nanofabrication. So I am Udiptya, doing my PhD at IIT Madras, and I am a PMRF scholar. We would be discussing some of the problems that might help you solving the assignments of the pertaining week. So I hope that you have gone through the videos already and must have been solving the uh, uh, questions maybe. So just a brief summary, just to brush up what were all the things and some of the like basic concepts that were involved in this. So the first thing was this comes under the broad category of additive processing. That is, we add some materials on our substrate. So on that, we are discussing about atomic layer deposition and physical vapor deposition. So under atomic layer division first video, we saw that how a sequential gas phase chemical process is used for getting atomic layers. So it's a self-limiting process that helps us in getting atomic layers. Second video was on was a continuation of atomic layer deposition. So we saw that how what is the deposition window. So the window like where we can deposit and depending on the temperature, like the temperature window where we can have our ALD done depending on the precursor that we are using. Now the nucleation aspects like how the growth happens, how these films are growing, and also advanced process that is a plasma enhanced ALD. Then we come to the next method of physical vapor deposition, in which we first video was on the getting the main crux of how the method works. So it was mainly the so it mainly is the process of physical transport of target material to the substrate and how we are forming a film through it. And the subsequent videos on deals with the two methods of getting it. So the first one is the evaporation, that is by thermal process, how we are getting the target material vaporized and vaporized and condensing on the substrate. And the last one was sputtering, like how we knock it off from the target material and get it on the substrate, right? Get it deposited on the substrate. So that's what we got in the this week 5. So we'll directly go to the questions then. So this is the first question that unlike CVD process, chemical vapor deposition, the partial pressure of precursors does not affect the growth in atomic layer deposition. So it's a true or false. You all can write whatever you feel the answer would be in the chat, and we will discuss it. False. Okay. Anybody else has any answers? So it can be it can be a guess, no issue. We will discuss anyways. Okay. So yeah. So so this is the thing that this unlike CBD process, the partial pressure of precursors is not does not affect the growth in ALD. So it is true actually, because the this diagram shows it that when they are flowing, when they are varying the vapor pressure of one of the constituents and keeping the other thing constant, the growth process is same. So in ALD, the partial pressure is not a determining thing, like in CVD it was. But the determining thing here is the temperature. So temperature is something that we control in uh, that we control and in ALD. So that that is something of an advantage in ALD that we get over CBD because here the like the things like the factors that are like variety of factors are there in CBD while the in ALD you can the factors that are there is very less. So it's the temperature that is something that can like change your growth rate like not the partial pressure. That's the crux of the question. So hopefully you got the thing, yeah. So if it would have been like varied with partial pressure, then the growth would have changed. Like it would have gone down or up, depending on it. How is it vary? Because the vapor pressure of the precursor in here is changing. So that is not the case. It's a self-limiting thing. So whenever it will stop, if you increase the partial pressure, you don't. So that's the thing. The growth will be same. So, uh, so this question from the like the deposition window that we go in ALD window. So in ALD, here we are like this is a process of tantalum oxide deposition. So we are using precursor and it is basically reacting with water. So the window is this. So uh, like here, when we see that the growth rate increases in this region, so this circle, this increases. So you have to tell what is the likely cause of this. What causes this increase in the growth rate? Ideally, ideally we want our ALD to be done in this window, but we see this kind of behavior increase, a sudden increase in our uh, the growth rate. So you can type your answers. If any like any other reason you think out of the like options that you also you can write, we will discuss. We can discuss on that also. So, so any answers? Okay. So, so, uh, so we get what is this one? The ALD process window. So this is the ALD window. So ideally, our reaction should be lying in this window for getting a self-limiting growth. Okay, but we see that sometime it overshoots. Uh, like depending on, and this window is something that we want, is the ideal one. But you see this characteristic is when we get an uncontrolled growth, and this is a case of thermal decomposition of pyro precursor. So whenever this this precursor lands on the substrate, and because of the high temperature, it pyrolyzes. So it's a kind of a pyrolysis reaction. So it breaks down on the substrate. So the thing is, if you think like this, it would eventually deposit on the on your substrate. Like it would land on your wafer, and it would it would coat, it would form a thin layer. But the main thing is, you want a atomic layers of tantalum oxide, not something that has been something that has been uncontrollably deposited. So this is what we are doing in CVD. So this is not a thing that we want. So we see that with thermal decomposition, like with this trend, we are seeing like this. So the answer would be thermal decomposition. The other things are like whenever like this process, that is uncontrolled growth, a precursor condense on the cold substrate. So because it is like vaporizing, it forms like something on kind of PVD. We see something like it. It condenses on the substrate. That is also something that is not ideal for atomic layer. And other thing is like this precursor, like we want some requisite temperatures. At very low temperatures, sometimes we don't get a reaction. So it is something to be taken with the Arrhenius reaction, that because it has an exponential like the Arrhenius one is K equal to K naught e to the power EA by RT. So it has an exponential relation with the temperature. So we need some like some energy, some temperature to get a reaction done. So that's and on some conditions you also will find like this. Uh, yeah, and sometimes you also get like this, the precursor dissolving. So at high temperatures, the precursor escapes the wafer. So the main thing is, in this condition we get the uncontrolled growth, and this would be the this uh, like this trend is shown when the sub precursor is decomposing thermally. Okay, I hope everybody got it. Okay, so we will go to the next one. So this is a question of characterization. So some of the characterization tools are given here. So out of the following characterization techniques, you have to tell which one of them would be ideal for understanding morphology and conformality. Like after doing CVD or ALD, how will you know that whatever technique, whatever you have done has got a like the required morphology or conformality? I hope you all got what is morphology. Morphology is like how the surface looks like, how there are some features, how the features are there, and conformality by means that like if you have edges like this, so how the thin film has coated on it, how conformal is. Like this can coat like this, or can have coating like this. So this says how it is that how the thin film, like this is the thin film, and that is the silicon, and this is the silicon. So this you would say more conformal. Yes, less less conformal. So like these things, how will you know which of the techniques would be a good technique, good method for understanding the things? I hope everyone understood the question. Yeah. If you have any doubts in the question, you can ask in the chat or you can unmute also and chat. So any other like any follow-up questions are also encouraged. So any questions you have, so we can discuss on it. Um, and if you have any other doubts pertaining to the course, that also you can discuss. So we can take it up in the end, and then we can discuss it. So so yeah, anybody? Okay, okay. Morphology means what? So by morphology we meant like how's the surface. So like you have some surface like this, and you have some surface like this. So this is what morphology means. The features, these are features. So how is the features there on the surface? So that something is morphology. Like you have one hole here on the surface. Consider these are something as a surface. Okay, this is a surface, and you have something surface, two surfaces. So so these are morphologically different. This is like this has lesser features, and these has more features. So all these things, these comes under morphology. How it looks, like how the features are on the surface. Some might have some, another one might have like this, some pill-like structure on the surface. So all these are morphology. So okay, we will discuss the answer then. Okay, no issue. So whenever we quote, like characterization is one of the, whenever we make anything, characterization is one of the important things. So, like synthesis is one another thing, and like we have to see how to characterize. Characterization means to be sure that whatever feature, whatever pattern we want, that is done. So, whatever, like each and every step must, in most of the techniques, each and every step is followed by a characterization to be sure, okay, this thing, whatever we have done, is being done perfectly. So we can't do like we perform on chemical reaction, and we have to be sure that okay, that chemical reaction have been formed. Okay, so like that, that is a characterization is something an exam uh, to see if the thing is examination of that material. Okay, X-ray diffraction. Okay, so we will discuss each and every option we will discuss. So no issue. So okay. So the okay, somebody has answered my X-ray diffraction also. Okay, no issue, no issue. So okay, let's take up option wise. So X-ray diffraction is one of the important characterization technique that we see. So in X-ray diffraction, we mainly understand the crystal or crystallinity of the materials. So most of the things like whatever crystal, so the crystallinity, okay, crystal crystallinity. So how are the crystal how crystalline it is. So and how are the arrangements? So you will get like 1 1 1 planes, 1 0 0, and all this, and the how is the lattice rhombohedral, and all this information is something you will get through crystallinity. So anything that related to crystals, like how the quality of crystals are and how all the information related to crystals is something we get through X-ray diffraction. Okay. So the second option is XPS. In XPS, we get the chemical informations like what is a stoichiometry. Like, okay, stoichiometry means that uh, I uh, I wanted to deposit silicon, but it wasn't pure silicon, but it was silicon minus X and kind of chlorine defects are also there. So, but I wanted this, but I got this. So, for understanding all these things, like what is the chemical formulations? Like I wanted to, like what are the chemical entities present on your surface? XPS is one of the important techniques, X-ray photoelectron spectroscopy. So, for understanding the scoitometry and the uh, chemical, chemical states or for states. So it is one of the important technique XPS. STEM and TEM is scanning electron microscopy and TEM is transmission electron microscopy. So these are two electron microscopies. So these are very important. So in out of this, you get a in this X-ray diffraction, you get a diffraction pattern. This you get a spectroscopy. But SEM and TEM are microscopy. So essentially, you are looking into some of the things. So that's where we get this morphology or we get conformality. So by looking at it, so looking at looking at some of the surface, we get that okay, uh, these have some surface defects or surface like some on like like some cave like this on the surface. So all these are something we get through same on time by looking on it. So microscopy is the important technique. So these have these are used for morphology. Though some crystallinity also we can understand some of the techniques like there are some techniques called HRTEM. So that also gives some information about the crystallinity, just how the crystal planes are placed. So you can also like get the crystal information from the HRTEM and also uh, like correlate with it with the XRD data. So that is something. So some amount of crystallinity informations are also visible. But most thing microscopy is powerful for understanding the morphology and conformality, obviously. Just by looking at it will have very good. You will see how the things have deposited on it. And SIMS, this you might have like undergone in the some of the techniques this is like while we're discussing about the defects, we discussed about SIMS, secondary ion mass spectroscopy, spectrometry, sorry. So in this we analyze the how deep the diffusion profiles. It is very good for understanding the diffusion profiles, how the materials have diffused inside. So we like on the surface we incident high energy beams, and after that some atoms are released from the surface. We analyze. We have a mass spectrometry, and we analyze the like the knocked off atoms. So by this we get the what is the so like you have this wafer, so you can start knocking off the atoms. You can go under it, so you can understand the whatever is down. So while you go down, you understand whatever things are there. So that is what we are. So the main crux is SEM TEM would be the answer. It is a technique that is very much used for understanding the morphology and conformality. Okay. Any doubts? So we discussed mostly all the characterization techniques that are there in the options. Hopefully, you all got it, yeah? Okay, let's go to the next question. So, in physical vapor deposition, we have a method of electron beam heating of so basically we have to heat the material that we need to be that this is the target material, so we need to heat it. So we have one mechanism such that so we basically heat the target such that it can release and sit on the substrate that where we want to be coated. So this is where we coat, this is where we want coating on this surface, we want coating. So we have to heat this surface. What is PVD? Physical vapor deposition. So the options are generation of argon plasma, magnetic focusing of electron beam, and resistive heating of filament. So so I hope you remember what is PVD, physical vapor deposition. So we physically vaporize and deposit on something. Physically vaporize it. So unlike chemical vapor deposition, we have a chemical reaction going on, but here we physically just most of the time whatever we want to deposit, we just physically vaporize and deposit. That's the thing. But in chemical vapor deposition, it was like we wanted A plus B to be deposited. So we will have a reaction between A plus B and then it deposited. So most of the reaction will happen on the substrate where you want the so A plus B will form a compound and it will sit on the thing. So that is CVD. CVD involves chemical reaction. Physical vapor deposition does not involve any chemical reaction. It's a physical process. So any answers? Any doubts in the questions? You can ask. No issue with that. Okay. Should we go on the answers then? Or you want to try something? Okay. Somebody wants to answer? So in physical vapor deposition, we usually have two types of heating. One is this one is something called resistive heating. So in this we have like so this is where we keep the material. So it is the material target. So yeah, this thing. So this is where we keep the material. So we will have a coil of resistor, and so current will flow, and so uh, this will be a high resistance wire, and it will produce heat. So this is resistivity. And another process is electron beam heating. So in this we have a electron gun here, and it will uh, it will go from here. So this focusing is done using magnetic field. So we can, that like magnetic field can change can change the path of a moving electron. So we mostly use this phenomena in a lot of applications. Like in we use mass spectrometry. We usually use this technique for like channeling the different ions, charged particles, and also in electron microscopy also we use this magnetic field focusing for getting a focused magnetic beam wherever we want this electrons can be focused on this. So this magnetic field is something that we help in focusing. So here also this electron gun is something that is releasing the electrons, and this magnetic field is perpendicular and it is focusing it on the this material where the target is present. So the electrons will hit it. So this will like cause the heating of this material, and thus it will release from the surface. Okay, and it will then coat on this surface. So generation of air plasma is not there. So in PVD, like generation of argon plasma, we would have ionized gases would be involved. So here no ionized gases are involved. So argon plasma is something that we are not discussing. Uh, Magnetic focusing of electron beam that we saw here is there. And the resistive heating of filament is another technique of heating. So, but this is not what we are discussing. So, yeah, okay. And I hope the things are clear. Okay, let's go to the next one. So, in problem 5, this is also a question from physical vapor deposition, particularly the evaporation PVD process. So, in this, uh, what is one of mechanism that helps in seizing, that is stopping the process of evaporation on a substrate? Like you are like think that you are ongoing, like uh, this is where target material is present. Okay, and this is where you want to be coated. So this is going on, and you are heating it. So some heat is also heat is also given. So you are heating it, and this is the target material. Okay, and it is going up. this molten material is going up and sitting on the surface. But you want to stop the process in between. So how shall you do it? So by cooling water, you mean that circulating uh, water on the target material, right? You cool it using cool the target material using cool water that is cool. So and others are some equipments that are part of the PVD physical evaporation equipment. So, so you have to tell which of the things can be useful for stopping the process of evaporation on a substrate. And then we will go on to the follow-up question that is written down. Anybody? I hope you got the question. Yeah. If any doubts in the question, you can ask. I can explain it again. Uh, but whatever answer you feel, you are free to answer it. So, and we can have some follow-up discussion on it, whatever, just to clarify your doubts, or maybe we get some another insights also. Okay, cooling water. Okay, any other people have any other answers? Somebody want to support him just to strengthen that thing, cooling water. Nobody? Nobody thinks cooling water is the correct answer? Okay. Others? Anybody? Up. I hope you all are here, not have just turned on the thing. And so it's not a typical class, so it's like you are supposed to interact, and whatever you feel, you are free to express. So okay, let's jump to the answer. Then we will discuss each and every step. So, so cooling water is something that is one of the essential part of PVDS system. So this target material, we usually when we heat it in electron beam, this get like this materials get heated a lot. So usually we have this circulation of cooling water in this pipe. Okay. So so it's something that goes on while the process is there. So something cooling water is something that is there. So if you recall, so you can see in this thing, water cooled earth. So cooling water is something you have to keep it cool such that only the material that is on the top portion of the thing is vaporized and it goes on the thing. The other part is something that remains cooler. Okay. So cooling water, uh, something that essentially does not function to stop to just immediately stop the process. So cooling water is something you have to do it all together. And if you remember, earth is something that holds the target like inside this thing. So this is the heart, and this is the crucible. Crucible is the basically the bowl that holds bowl or any other, like you have multiple shapes for your sense, like bowl won't be a correct thing. You have bowl like kind of bowl like structure or kind of boat like structure. A lot of depending on your use, you will have crucibles. So these crucibles and hearth. So one of the option is hearth, and another option is the crucible. The main thing is the shutter. So shutter is something that is a physical barrier. So this kind of a blocks it. So it just enters, like it enters the thing whenever you feel okay, I want to stop. The shutter will enter in between the path and the uh, break the like till now not reach these vapors will not reach the substrate. That's how the evaporation process would be stopped. So this is something that is the function of a shutter. The shutter is something that will just physically have a barrier between your uh, the target and the substrate. So for a clearest, substrate is something where we are depositing our materials as the substrate, the target. I hope it's clear. The shutter is the correct thing. And like this stopping you will do because like I wanted 10 nanometer thickness of my material, and I got 10 nanometers, so I want to stop. So it's you won't stop like just something. You have to like you will have some decision to make. So in like while this physical deposition is going on, how will you get to know the thickness of the film? So this is the substrate. So how much thick this film is inside the chamber? So it is not like you can't take out the wafer and see in electron microscope. That can't be done. So inside, like inside, it is this is target, and position is going on. So how will you monitor the thickness here? So if you have any idea, so I didn't add any options here, but if you know any method how this is done, this would be super. Anybody have any answers? They can tell. We will discuss anyways. So this is something that is used to measure the thickness. So whenever we get the requisite thickness, we will just stop it using the shutter. So anybody knows what is the instrument that is basically used for like, uh, predicting the thickness of the material or measuring the thickness of the getting an idea also how thick is the material, how much of the material has been deposited on it. So okay, let's go to the answer then because time is something that I running out of. But so uh, you might have heard something about the quartz microvalence, quartz crystal microvalence. So if you have heard, these are some piezoelectric materials. Okay. So piezoelectric materials. These materials, when we subject them to a voltage, they tend to uh, oscillate in a defined frequencies. So it will have some resonant frequency. It will have a frequency. Okay, and so this is something. So you can assume like a plate, and this will uh, this will oscillate in a defined frequency. Okay. So the thing is, it is placed inside the chamber. So whenever any mass lands on it, or any mass left from the surface, this resonant frequency will change. Okay, so that's how we will get how much is the added mass. So this is placed just like, like in this figure, it will be placed here, assuming it is placed here. So whatever material is deposited on the substrate, it is the same material is also deposited on the sensor, this quartz crystal microbalance sensor. So uh, this added mass changes its resonant frequency. So it will now like oscillate in a different frequency. And by that, like we have some like the computer can then process, okay, we have got this much mass and this much mass is related to this much this much growth of film. So that's how we can understand while we are doing the process of evaporation, how much of the material has deposited. So this quartz crystal microbalance is something that is placed inside the chamber just to know how much we are getting the thickness. Okay, so let's go to the next one. If any doubts, you can ask. So this is problem 6. So this is a diagram that you must have seen while in the PVD section. So while PVD we are doing PVD, we have so these are three zones, and the three zones have different temperatures. Like these are TM here means the melting temperature. So like less than zero point 0.3 melting temperature, they get like this. 0.3 to 0.45 melting temperature, they get like this, and more than 0.45 melting temperature, we get like this. So while doing PVD, whenever we subject it to these temperatures, melting this degrees of melting temperature, it has different crystallinities. So you have to tell which of the following is the increasing order of crystallinity. So essentially, the temperature, like if you have T1, T2, and T3, like maybe the this thing will okay, TA, TB, and TC. So essentially, TA is okay, sorry. The TA is lower than TB and TB is lower than TC. Okay. Somebody has answered D. Okay. Others? So you have to tell what is the increasing order of crystallinity. So crystallinity by crystallinity means ordered structures. And opposite of crystallinity is amorphous. So it will have no order. Anybody else? Anybody else has any answers? Okay. So we know that usually when the temperature is low, the materials tend to like while like procedure like PVD is done, it will set, and wherever it lands usually it will stay in that position. So some of the temperature is needed to for it to be diffused such that uh, they can have a ordered orientation. Okay, so mostly it tends to be in the higher temperature. So higher temperature will give them some like while we were discussing about diffusions, the diffusion is tends to be like it happens when the temperature is high, the diffusion happens very fast. So while this like here we see that the temperature of C zone is highest. So here uh, it has more energy for the atoms to be rearranged. Wherever he was, it can rearrange. So C would be the most crystalline one, then the B, and then the A. So A, B, and C. So A, which option is this? This one. Okay. Any doubts? You can ask. Okay. So this is problem 7. So we also discussed DC sputtering. So by sputtering, we mean that we are knocking off. So sputtering to be like just for a recall, sputtering is something we knock off the electrons and knock off the atoms, and by having a DC. So so here we have two electrodes, and we like have a DC bias here, and uh, by this we generate the electrons, and usually it is done in the presence of a plasma. The plasma is present. Uh, so it this plasma is this is argon plus. So this is the negative terminal, and this is the positive terminal. So this high bias gives rise to this argon ions, which we call as plasma. This plasma energy comes down and releases, like this is the high energy plasma that knocks off the atoms from the target material, and it goes to the source, others to the substrate side. So this is the concept of DC sputtering. Now you have to tell what is the uh, what is the its relation to the distance between the electrodes and the argon pressure. So two factors are there, and it can be a multi-correct. So uh, kindly see whichever is correct. So then we will discuss the answer. So anybody? So this distance between the electrodes we are giving L, and the basically we have an inlet of This is a chamber, vacuum chamber, and we have argon gas coming out, coming. So, and this somewhere you will have this is a complete chamber, and like out. So in this chamber, what like how these two factors, the AR pressure, argon pressure, and distance between the electrodes. This one, the two electrodes, how it can affect the TC. But deposition rate. Okay. Nobody has any idea. Should we go to the answer then? A. Okay. Okay. Anybody else has any answers? Any guesses? Okay, let's discuss the answer. So here we see that so just simplifying the things, we have two electrodes. Okay. So okay, A. Okay. Okay, A has two supporters. So let's see the answer. Okay. So so this is where we are starting from. This is where we want to reach. So this is the goal line. So you can think that okay, this rate whenever it is going far, like this is going far, should like you have now the materials have to run a more. Okay, like if it is now here and we are increasing the distance, it's going far off. So it has to now attain a more higher distances. So this is something. So in between, it can also get lost. Also, like it can go this way. Materials can go this way. So essentially, when the distances increase, now you need more. The materials now have to attain longer lengths. So it is something that decreases the deposition rate. So essentially, it would increase because you have to now go more. Okay, and in between also, if it can deviate here and there because this it can uh, like collide with other air molecules which are present, and it can like deviate. So whenever you are increasing the distance between the electrodes, the probability of it reaching it decreases. So essentially, you are decreasing the deposition rate. So unlike A, the answer would be the B. It is inversely proportional. So uh, okay, sorry, I didn't add L. That is something that I missed. So here, the distance between the electrodes will be inversely proportional to the no, this one, sorry. Inversely proportional to the distance of the electrode. So unlike A, directly proportional, it will be inversely proportional. Okay, sorry. And regarding now the thing is the AR pressure. So whenever this pressure increases, like now, if we have lower pressure, that means we are going down to, we are going more vacuum. So in less vacuum conditions, we usually have less mean free paths. So when we have less mean free path, essentially we mean that whatever we want to like deposit, we will have now molecules that like it will have less molecule, less mean free path. By less mean free path, it means that it will collide with a lot of materials, lot of molecules, and by this, it the thing reaching it is very hard. Wherever when we have higher vacuums, like when we have like less vacuum of argon pressure, it will be very like it will be empty more or less. So it can directly reach here. So it is inversely proportional to organ pressure. So this is B and C is the right one. Hopefully I'm clear, yeah. So okay, I think we have more or less completed. Okay, let's stop the session here because time has been there. So